All right, so I'd like to welcome everyone to today's roundtable, the joint roundtable between BNL, JLab, and the HEP Software Foundation. Today, we've got a really interesting set of talks, all centered around the topic of data on the network. So with that, we'll begin with our first speaker, who is Andrew Hanushevsky. And Andy is an information systems specialist at the SLAC National Accelerator Lab. After joining SLAC in '96, he developed BBCP, which was a popular peer-to-peer file copy utility, followed by the XRootD framework in collaboration with INFN Padua that was developed to provide high-performance network-centric data services for the Babar experiment. Since that time, XRootD really has become a widely used framework for third-party data delivery solutions throughout the HEP and now also the astrophysics communities. Andy also serves as the architect and lead developer for the international XRootD collaboration at xrootd.org. And he graduated with a master's in computer science from Cornell University, where I believe we crossed paths probably much longer ago than I can remember.
That's probably true.
Yes. So with that, I will hand it over to you, Andy, who will be telling us about a number of the new features that are coming up in the XRootD 5. Please,
Well,
Andy,
actually, it's not so much new features. I looked and said, what I really should do is describe the features that are there and some of the new features, because most of the features I'm going to describe people are not aware of. So let's get started here. First, just a reminder, what is XRootD? And I just want people to focus that it's a system for scalable cluster data access. And it always comes together with an XRootD daemon, which provides the data access, along with a CMSD daemon, which does the data clustering. And we just marry them together to actually provide the whole complete system. You can run XRootD without the CMSD if you don't need clustering, but many people do use the CMSD for network scalability. So XRootD is really not a file system, and it's not just for file systems. In fact, people use this now to cluster practically anything. And it doesn't have to be file systems. It could be, for instance, like Rubin Observatory uses it to cluster MySQL servers. Now, the notion is, how do you provide scalable access? This is just a little bit of an example. We have here a list, a tree of nodes. These nodes are arranged in a B64 tree. The reason we choose that is it just makes routing a lot faster. And also it has a huge scale out. So you can see once we have a 2-level tree, we can support 4,000 servers. So the task here in this little video sort of presentation is to route a client request from the top of the tree to a resource provider, which is at the bottom of the tree. And so the client issues an open request to the manager, which is a redirector. And then the manager does an exponential parallel query to find out where the resource is in that tree, and then caches the paths to get to that resource along all the routers. Now, which ones are the routers? Anything that says redirector is essentially a router. So it goes back to the client and says, oh, by the way, this is your next hop that you need to go to. That hop says, oh, look, I just found you basically a resource provider, and the client goes off and does whatever it needs to do. Now, this is very different from traditional data management models. And so it implements really a structured network of request routers, which here are called redirectors. And they're also capable of automatically recovering from adverse conditions, which you'll see just in a second. But the big important thing here is essentially works much like internet routing. In fact, the algorithms used inside the CMSD are pretty much what you'd find in a router. But the big difference is this actually practically implements a named data network. So let's say that server went away, and now the client goes and tries to find an alternate path, and it'll just go through the same sequence, but it'll be routed to a different data access provider that is still working. So that's how the whole scalable access works. So a little brief history of the last 20 years. Yes, it's amazing that XRoot has been around for 20 years. Uh, and it starts off in 2001 when Babar decides to use the root framework versus objectivity. The following year, we establish a collaboration with INFN and develop this network-based high-performance data access system. Now, one thing to remember in that day, which people forget, we really had limited bandwidth, and it really had to work very hard to utilize that as best as we could, because frankly, increasing bandwidth in those days was very expensive. So in 2003, the first deployment of XRootD system at SLAC. A decade later, the wide deployment across most of HEP, and even the protocol was re-implemented in Java in Dcache, which is there to this day. And then a decade later, almost now, XRootD becomes a popular internal framework for third-party software. So it's got this moniker now that when you see a system, you look and say, oh, it has XRootD inside. So let's look at the network-oriented features. The design goals were fairly obvious, right? You want to minimize the bandwidth usage, which means don't send any unnecessary data on the network. You want to maximize the bandwidth utilization. Whatever bandwidth you have, you want to use to the fullest extent. And you want to work around network and server failures with automatic recovery whenever possible. But most importantly, you want to be flexible, because the network configurations always change, and you want to be able to adapt to that as much as you can. So let's see what we did here. The network bandwidth usage. Right off the bat, we designed a call to essentially have incredibly low framing overhead. And as you can see, it's probably the lowest around, with 24 bytes for a request and 8 bytes for a response, which means we achieved basically that 99.99% of a packet is application data. Now, some people say, well, it doesn't matter. Well, it does matter depending on who you are and what you're doing. Of course, if you sell bandwidth, it's a lousy protocol. You want it to use as much bandwidth as possible because you're selling it, right? But if you're buying bandwidth, it definitely may matter. And what you're doing, if you're doing random size reads, it likely does matter. And that's something that's very typical for many HEP and astroanalysis jobs. The actual amount of data that gets transferred today is somewhat larger than what it was in the day 20 years ago, because a lot of these applications were transferring anywhere from 256 bytes to 1K at a time. So you really needed a low framing overhead. But if you're transferring a multi-gigabyte file, that doesn't really much matter what the framing overhead is, because the file is going to dominate everything. That said, because of these features, the protocol can easily fill a 100 gigabit pipe. And that's been shown actually at CERN, that they can fill their 100 gig links with just a few actual parallel clients. And that's important to realize, because if you try to measure this on an individual transfer, you won't necessarily fill the pipe if the architecture of the server favors aggregate performance, which is what we do. So the other way that you can limit bandwidth usage is this component that we have now called XCache. Which is very similar to a SQUID, but unlike SQUID, it provides high-performance multi-threaded disk file block caching, something that SQUID was never designed to do. It's suitable for locales where data is reused, which is typical in analysis farms that fetch data over the WAN. And it's actually interesting to see that some sites have actually seen a 40% reduction in WAN usage when they're using XCache. In practice, on average, you shouldn't expect more than a 20% reduction in a typical use case. Now, there's really two factors in HEP that make XCache useful. And that is because many applications use a very small part of the file to do their analysis, and XCache only transfers the part of the file that the application needs, as opposed to the whole file. And analysis jobs are also run several times with different parameters, and much of the same data is needed on a subsequent run, and whatever is missing gets fetched for the application. Now, if that isn't what you're doing, then XCache obviously is not going to help you much. Now, there's another aspect of how do we use LAN resources better? And this is specific to high performance computing centers, which have this usual setup that they have a Lustre system that has RDMA access to all the nodes in the cluster. And the cluster also has a TCP link, but it's not all that great. So what they do is they set up an X cache where the cache actually lives in Lustre. And as the analysis job starts, data is missing. It gets fetched through the DTN, placed in Lustre, and also delivered to the analysis job across the slow TCP link. But once the file is fully cached in Lustre, then the client is redirected to the actual file system, and then all the data then proceeds into the analysis job using the RDMA channel. Now, the other one, which is interesting, and some people might want to follow this up, but maybe not, the protocol actually supports data compression. Now, that's a legacy feature from Objectivity DB, because in the day, we wanted to minimize disk space usage because that was expensive as well, but it also reduced bandwidth usage. And so we only sent compressed data over the network, and the client would decompress the data. The feature has fallen to the wayside because people have gone on to the root files, which are already compressed. So you don't get much gain by compressing the data. It's interesting that Objectivity DB files actually had a huge compression ratio, typically 2 to 3 to 1. Now, for certain file formats going into the future for other communities other than HEP, it still may be useful, and the protocol does enable the feature on a file basis. So you could restrict it to certain file types. So some file types would be compressed and other ones would not be. But we would need some more development to actually revitalize the feature because currently we just don't support it anymore. Now, additional one in XRootD 5, which is a new feature that got put in, is we added data in motion integrity. That was largely driven by Xcache requirement to avoid caching dirty data, which is sort of sticky. Once you have a dirty block in the cache, it's a little difficult to get rid of. So when we transfer the data, each 4K block is protected by a CRC32C checksum. Now, we chose CRC32C because it's hardware assisted and actually runs pretty fast. I mean, really fast. And it works out that actually CRC32C is pretty good in catching errors in 4K units or smaller. So checksum errors are corrected on the fly because we know when we receive data, it's either good or bad. So when a client is reading data and it finds that it read a bad block, it requests the server to retransmit that block. And when it's writing data and the server receives a bad block, it'll ask the client to retransmit that block. Now, data in motion integrity has the potential to save a significant amount of network bandwidth. So imagine you're copying a 100 gigabyte file and there's a 1-bit error somewhere in there. What do we do currently? Well, we transmit the whole file, we run a checksum on the file, we find out that the file is bad, and then we have to retransmit the whole file again. With this feature, you only retransmit the 4K block that it's an error. In this case, if it's a 1-bit error, it's a 4K block overhead to get the file in a good shape. And of course, the next question is, well, how often do network checksum errors occur? Well, unfortunately, that's a statistic that really is not collected. Now, informal observations indicate that it's variable. Sometimes you get a lot of checksum errors, sometimes none. It's not a constant thing. But when it does happen, it can be significant. And what does significant here mean? It can impact more than 1% of your transfers in the period where it's happening. Now, while that's great to say, it's also difficult to capture because checksum errors are somewhat indistinguishable from disk errors without having data in motion integrity. But now that we have that feature, we can actually distinguish between those two cases, whether it's your disks that are a problem or it's the network that's the problem. Now, we also provided on top of that data at rest integrity, largely for Xcache. So we actually can save the network checksums that we get that are good. And then when we read back from the disk, we can use those checksums to verify that nothing bad happened on the disk. And the other nice thing is when we retransfer the file, we just retransfer the checksums along with the data and let the endpoint check that everything went okay. That way we don't have to keep recomputing checksums. Now, in terms of data utilization, so XRoot supports multiple data streams. It has for quite a while. An application can get up to 15 additional data streams, and that's good for improving the speed of WAN transfers. That's been well documented, and it's used to mitigate TCP recovery for dropped packets, which is why you get better performance. Now, multiple data streams is a new feature in XRootD 5 or its use in mitigating TLS performance issues. So the protocol, unlike many protocols, naturally splits into a control stream and a data stream. And us splitting the protocol that way is automatically handled for the application so that you don't have to encrypt everything. You can just encrypt the control stream and do not encrypt the data stream, avoiding TLS overhead for stuff that just doesn't need to get encrypted. Now, mind you, that a site might require that all data be encrypted for privacy reasons, and that's negotiated between the client and server. The other big thing, which is also network-oriented, you'll see why, is container orchestration support. So XRoot does support container orchestration. The typical ones that are being used today are Kubernetes or Swarm, and both introduce issues for network clustered services like XRoot. And the reason is because of virtual networking, where the IP address is arbitrary and can unpredictably change. The other reason is because of dynamic DNS, where IP addresses are registered and removed at a whim's notice. So registration essentially is ephemeral. Supporting orchestration requires some rethinking on how you're going to do that. And so XRoot provides configurable options to address the issues introduced by orchestration. So one thing to remember that essentially when you're orchestrating containers, the IP address is no longer a useful management tool. You just cannot use it for anything except to getting to someplace. So virtual networking support. When you see a virtual network and you're trying to do something like a named data network, you're going to need a virtual namespace. And XRoot implements such a namespace. A site essentially assigns accessible resources on their whole cluster, relative unique names. So normally when we think of a resource, we think of it as a server, but that's really in an orchestrated system no longer relevant. So imagine that you're actually trying to serve file systems or data on file systems. So in that case, the resource really is the file system, not the server. And why is that? Is because in an orchestrated system, any server can export any file system. The server is really immaterial at this point. So we really need to track file systems now, not servers. And for non-data services, like something that you might do with the scalable service interface, it's usually the server. But in the main case of file or data access, it's the file system. So the clustering component now tracks resources by name, not IP address. That also allows it to make sure that the XRootD component is actually looking at the same file system that the CMSD component is looking at to make it all consistent. And why is that important is because in an orchestrated framework, it is so trivial to pair these things up with different file systems. And when that happens, of course, all hell breaks loose. So we now have a consistency check to make sure that everybody is looking at the same thing. Now, that said, we don't recommend virtual networking due to overhead. A lot of people do like it. I will say that commercial cloud providers have substantially reduced the overhead of virtual networking, but typically open software solutions have not. You can get up to a 20% hit by using virtual networking. In terms of dynamic DNS support, so in an orchestrated framework, DNS entries are a spur of the moment thing. The orchestration framework registers IP addresses whenever it needs to. It doesn't care what the order of the servers are that come up. So you really can't depend that an IP address that you see is actually registered anywhere. So if you tell XRoot and the CMSD that you're using a DNS that's dynamic, then we enable mitigation for that, which is what mitigation for delayed registration, that avoids the failures that you would normally see in a real network, where you configured server X, and then we say, oh, where is server X? And then we don't find it, and then give you an error in a real network saying something's wrong with your configuration. In an orchestrated framework, we have to allow that maybe server X isn't up yet and hasn't been registered. So, so that's how we support dynamic DNS. So in the end, XRoot is actually very comfortable in the cloud. And so sites have deployed cloud clusters by just using these features. Other net-oriented features where we have fledged clustered proxy server support, and that also people scale using the clustering framework, so they have multiple proxy servers, and it's actually, they do it to be very sensitive to which load is occurring on which server, so we can spread the load evenly across those servers. We also have configurable TCP keep alive support. On top of that, also idle sock out timeouts, which typically occur in certain VM configurations where sockets wind up in closed wait. We also have full support for public-private 4.6 IP networks. This is sort of an interesting one that we developed, where essentially that's used by the clustering component, and you you basically describe in the configuration file IP address rules. How do public-private 4.6 IP network rules actually work in your site? That allows us to automatically match compatible addresses for routing, which actually winds up being a very difficult problem in HPC centers. And we can also use that information to minimize the number of internal network hops, which is also very important in HPC centers because they really wind up doing these weird network combinations to actually get the best performance they can out of the network. And we have to be able to basically work with that. And that includes using preferred interfaces whenever possible. So that kind of support is now currently used at GSI to really make complete use out of their network. We also have enhanced write support. That is actually a new feature. That's distributed write recovery for files, for systems that support it. Now, typically when you start writing a file, the basically says you are bound to the server you started writing the file at. If that server goes down, you have to reconnect to that server to continue writing that file. Now, not all systems have that constraint, and new in release 5 is the ability to basically say, no, you can start writing to a server. If it dies, you can go back to the redirector and say, please give me another data server to continue writing. And you'll get another server and then continue recovery at a different server. So that's part of the file copy framework, which means that it automatically gets supported in GFAL and XRDCP. Some performance improvements in XRDCP, there was a complete rewrite of how buffer management works in trying to use kernel space buffers. And once that occurred, we actually saw a 3 to 4x reduction in CPU usage, but more importantly, we saw up to a 40% increase in transfer speed, depending on what your target device is. Obviously, you will not get 40% unless you're using something like an NVMe. The other one we have, which is coming soon, Xcache H plugin, and that is using Xcache, but where the origin is using HTTP or HTTPS protocol. So this broadens the data access reach. It's oriented toward multidiscipline sites, not necessarily HEP sites, but interestingly, it can be used as a SQUID replacement for better performance and scalability. That was based on a plugin way back by Radu Popescu from CERN, and was further developed by Wei Yang at SLAC. And right now, that prototype is being tested at ESnet and Escape project. Another one coming soon, which is interesting to a lot of, and that is a client-side support for EC writes, erasure coding writes, and that's based on Intel iCell hardware accelerated encoding. That basically leverages the XRootD PG write capability, which is the data in motion integrity with recoverability. And is driven by Alice requirements in this case, where they need the performance from the DAC system to write it to the file system, in this case EOS. And so they basically need to write erasure encoded stripes directly into the file system as opposed to doing one additional hop. And that was developed by Michal Simon. Some other developments coming soon, improved Ceph plugins. That's being basically driven by RAL, and part of that includes vector reads and write supports for Ceph. Packet marking, labeling the purpose of data in network packets. It winds up that XRoot will be used as a demonstrator to show that this is actually useful. The big qualification here is it's only useful for IPv6. And a lot of people are moving to IPv6, but the moment you start doing orchestration using Kubernetes or virtual networking, that whole idea goes out the window and it's not particularly useful at that point. So what's the conclusion? XRoot is facile, flexible, and sound. It's actually pretty solid. And it's applicable to a wide variety of problems. The current release is 5.1.1. The next release is going to be coming out at the end of April, 5.2.0. So while this talk was network focused, and I talked about all the networking features that XRoot leverages to put data on the network, XRoot actually has a huge number of other features. So you can check those out at the website XRootD.org. And that's the end of the talk.
Andy, thank you so much for this whirlwind tour. Really covered a lot of interesting ground here. And I think even though we're running a little bit past, let's take a few questions. We did have a question in the Google Doc from Doug Benjamin. I don't know, Doug, do you want to jump in here?
Sure. Thanks for the animations, Andy. But my question really is, can that Xcache be told to pre-fetch the data, especially in the HPC use case?
For the HPC use case, you turn on aggressive prefetching. So it actually winds up prefetching most, if not all, the file before the application ends. But
it does. You can't prefetch before it actually starts up, so you don't have a delay at the beginning if you don't have the data.
No, we do not yet have the capability of forcing a full file prefetch. On the other hand, I mean, you could conceivably just run an XRDCP through the cache to make sure that the file is there ahead of time.
Yep. Okay, thanks.
Okay, thanks, Doug. Looks like we also have a question from Richard Jones, a very important question about site tokens. Richard, would you like to jump in?
Yeah, I just wanted to say that we use our XRootD is all through Dcache in our experiment because it has a very efficient way of handling the initial connection GSI. It caches the answer. But if we try to switch over from reads to writes, the writing has to renegotiate it on every connection, and it becomes a limiting number of. We get limited to just a handful of files per second rather than 100 or so, which is what our present read rate is. Can you tell us about direction in the authentication layer?
So first of all, the GSI is implementation specific. So in XRoot, the GSI implementation wouldn't have that problem. In Dcache, it's a completely different implementation.
Indeed.
And I don't know where that issue is coming from. We worked with the Dcache team to make sure that what they implemented was very similar, if not identical, to what we implemented. That doesn't mean that actually happened. It's certainly identical in terms of protocol on the wire, but what happens internally after the authentication happens is a black box for us. So that may be a problem with the implementation, not a GSI specific thing. In terms of long-term, okay, we support PSI tokens in the XRoot protocol. It's been in the HTTP protocol for some time now. And we know that the move from X509 to PSI tokens is going to be a multi-year effort. It's not something that is going to happen on day one because there are actually quite a few nagging problems still left in using PSI tokens. Right now, they're used basically for a third-party transfer. And that seems to work reasonably well because that's very tightly controlled between FTS and the endpoint that you're copying from or to. So there's not a big problem there. But in terms of general usage, right now, I think they're figuring it won't be out in, this is OSG, mind you, it won't be out until about 2024. That's how long it might take. Does that answer
You're
your
muted,
question?
Richard.
Oh, I'm sorry. Yeah. So to be clear, that those PSI tokens that are being used in third-party transfers are the ones that are owned by the services themselves, not presented by the user, right?
Yes, correct.
Thank you.
All right, great. Thanks for that question. Andy, I also had a question about that. Found that data in motion integrity feature very interesting. Do you have monitoring of the correction rates? Have you seen?
No,
what's been done
because
on
the monitoring is will be there. Okay, it just hasn't been implemented because we're arguing amongst ourselves how it should be included in the monitoring packages because it's not exactly 100% upward compatible. And so we have a problem there. In the Xcache side, that would be recorded for Xcache, which sites have packet loss or packet problems in terms of corrections, but the client isn't yet sending that information to Xcache. So once we have that in place, then the monitoring stream from caching servers will tell you which sites have problems in terms of checksum errors.
Okay, yeah, that would be very interesting information. Thank you very much. Are there other questions before we let Andy go? Please feel free to raise your hand or jump in. Okay, if not, then Andy, thank you so much for this very interesting talk. And it'll be interesting to see, as the nuclear physics community continues to develop these experiments, what role XRootD will continue to play. Thanks again. So with that, we will move on to our second speaker of the day, who is Chin Guok. And Chin is the Planning and Architecture Group Lead for ESnet, which is, in case you don't know, DOE's high-performance network user facility. He's been involved in network engineering at ESnet for over 20 years, architecting specialized overlay services within the ESnet production backbone, prototyping software-defined network production solutions, and facilitating design and architecture work. Currently, he serves as the lead architect for ESnet's next generation network, ESnet 6, which is due to come online in 2022. And we are very pleased to have him here today to speak about building a data infrastructure from a WAN provider's perspective. So Chin, please take it away.
Great, thank you. Can you guys hear me okay?
Sounds good.
Perfect. All right, so I'm gonna give you a WAN provider's perspective on looking at what it takes to build a data infrastructure. So it's gonna be reasonably high level, but we will talk about some specific activities that we're doing. But generally, there are three areas that we want to focus on, right? So the first is capacity, and the general idea there is, putting the right amount of capacity in the right place at the right time. The next thing that we want to look at is capabilities. So building capabilities, is essentially, looking at services that are not just data transfer services, right? They're more data infrastructure services. And then the last one is coordination, where the idea is that, if you have all this capability, right, how do you actually orchestrate this so that you can come up with an end-to-end solution? So I'll kind of talk about these three different aspects and some of the activities that we're doing. So the first one is pretty simple. We talk about capacity. There is this notion of capacity planning. Since the 1990s, we've seen about a 55% growth year on year in terms of traffic utilization. As you can see, in 2019, there was a downturn due to the pandemic, but generally, we've seen exponential growth that is consistent through the lifespan of ESnet. So based on that, for ESnet 6 that we're currently deploying, we're actually building out additional capacity. And so this is kind of what the planned capacity will look like for FY 2022. Essentially, it is anywhere between 3 to 10x of what our current link utilization capacity is. And so we're looking primarily at 800 gigs to 1.2 terabits per link on between adjacent devices. Next, I'll talk about capability. So this gets a bit more interesting. These are some of the things that we're kind of exploring. None of these are production services at the moment. So, a lot of it is basically investigating prototypes, feasibilities, and things like that. So the first one I want to talk about is in-network caching. This was done essentially in collaboration with UCSD, USCMS, and the Open Science Grid. And the basic idea was to understand how much network utilization savings do we get out of these caching solutions, as well as the overall application performance. These are kind of a couple of graphs that kind of give you a summary. So the pilot ran between May and November. There was a month, if you look at between mid-September and mid-October, there were some hardware issues on the host that we had to work on, and so it was offline during that period of time. But generally, we have about 6 months worth of data. These graphs actually shown to are drawn to scale in terms of relative to each other, and so you can see that based on the in-network caching solution, we're able to get pretty good results, right? Essentially, we saw a network demand reduction of about 3. So there's a total of like 168 terabytes worth of data that was actually pulled. There were cache misses and about 322 terabytes that were cache hits. In terms of, if you look at the file reuse rates, what you actually see here is, a file in general, the file reuse rate across all the unique files on the system was between 2.5 to 3. And so it's pretty significant in terms of how much bandwidth we actually can save, right? And it becomes key to ESnet specifically because we do have transatlantic links, which essentially are significantly more expensive than the links that we have on the continental US, right? And so reducing the bandwidth requirements on those links significantly change our cost profile. This is just kind of a summary of what I mentioned. Essentially there was about 1.2 million accesses over the period that we ran the pilot. There's a network savings of 3x. So it's proven to be reasonably impactful that we're actually going to be deploying 2 additional caches in summer, right? The current cache actually is is located in the Sunnyvale area. The way it's deployed is a bare metal system that essentially we allow OSG to manage. And so what we're looking at is 2 additional caches, and this will be actually distributed somewhere between, somewhere on the East Coast to kind of give us better coverage in terms of understanding how the data movements are being utilized. And so there will be 2 additional studies that we're looking at. One is the cache miss rate, and the other one is the cache utilization. Now, I'll kind of move on to this thing, which is a prototype service that we're currently building. And so, based on the usefulness of the caching, the in-network caching solution, we've kind of thought one step ahead, where in terms of the current deployment, where I talked about it being bare metal, the issue is that it's not scalable if we wanted to start engaging other science disciplines. So, for instance, if we're looking at things like the genomics or climate, what we don't want to do is to basically deploy discrete bare metal systems for each in-network caching solution per engagement. And so what we're looking at is a solution that allows to virtualize that, and essentially allows to manage it in a way that provides us the ability to be flexible and to engage and dynamically create and take down these services. So we do actually have a prototype that we've built. It is basically based on containers. We have a centralized host that manages the container systems, as well as the software that is implemented on top of that. In the spirit of eating our own dog food, we're actually transitioning our current 10 and 40 gig testing DTNs to this DTN as a service. We've actually deployed the DTN as a service infrastructure on our testbed to manage images, just to ensure that we understand how we can manage containers and enforce security. And in addition to that, we're also evaluating different data mover software stacks, such as Zetter. And what we're doing is we're actually actively engaging the different organizations in order to determine if we can actually deploy DTN as a service as something that they would use. And so we've currently been engaging JGI, FRIB, and MSIL. Right. Now I'm going to change gears, and I'm going to talk about edge computing. So the activity that we're doing with edge computing, this is highly, this is really nascent right now. And so a lot of what we're doing is to understand what the workflow looks like, where potentially, our participation would be. So this is just to kind of give you a general idea, where today, this is the general framework of how we see real-time workflows being executed, right? So you have an instrument on the left, you have a first set of hardware that takes the raw instrument information and then essentially converts it into the digital domain. And then you have this middle portion where you do the data acquisition, data reformatting, you do some pre-filtering, stream assembly, and you essentially package it up to send over the network so that it can actually be either stored or computed against, right? And this middle function is typically built out of servers running potentially some GPUs, and in order to keep up with the high throughput, it has a whole bunch of 100 gig NIC cards. And so what actually happens is that you have a middle system that is reasonably expensive. It's general purpose computing with GPUs, and so there is some flexibility, but the fact is you don't need that much flexibility. There's a very specific set of functions that you want it to do. So what we've been looking at is to actually change that out and say, hey, why don't we actually use FPGAs instead, right? They're dedicated systems, they're reasonably flexible. You need to have the expertise to develop the right, the right coding blocks. But generally, once they're done, it's a highly efficient system, and it's low cost and scalable. So that is one area that we're kind of exploring right now. We're actually working with some of the folks. We've had some initial engagements with the folks at JLab, specifically, I think it's Michael Goodwin. And also we're looking at putting an additional function at the compute side. And the idea there is, to allow you to utilize the link in the best way possible. So today, when you do the data acquisition reformatting and the stream assembly, when you send it out on the network, you really want to have it in sequence so that when it comes to the compute side, you can reassemble it and it's ready for either processing or storage. But if you want to utilize the links in the middle and you want to be able to have more control, then you may want to bookend it with a function on the far side that allows you to do out of order reassembly and potentially even some local compute load balancing. And what this actually does is, it takes away the requirement for you to run any kind of, standard protocols. If you want to run something more efficient, right, you have control on both sides of the link. And so this is another area that we're currently exploring right now. Right. And third, I think I'll talk about coordination. And this is kind of interesting because what actually happens is that, the current situation is that the network is often seen as a black box, right? You throw packets in, it comes out at some point in time. You think of it as best effort. Sometimes it makes it, sometimes it doesn't. So what that actually does is it prevents you from building a end-to-end workflow that has guarantees in it. And so to overcome that, the idea is that, if you are able to coordinate with the network or resources that you need to use for your pipeline, all of a sudden you have these guarantees that allow you to make to run a workflow with a much higher tolerance because you have these guarantees. And so that was the motivation behind, this software that we wrote. So it's called Sense, SDN for end-to-end network science at the exascale. The whole idea is that the application workflows can actually talk to Sense and coordinate resources for an end-to-end solution, right? So it's intent-based. We have this whole notion of resource discovery. There's some monitoring, troubleshooting capabilities. And the whole idea here is that it provides you with deterministic networking. Since the architecture really is broken down to two components, we have the orchestrator, and then we have the resource managers. So the orchestrator is essentially tied to the application workflow. The idea is that you may have a orchestrator for CMS, one for, for genomics or something like that. The orchestrator deals with the northbound API that allows you to customize it based on whatever your application workflow is. On the back end, where the orchestrator talks to the network resource manager, we have a set of standard APIs that we use. Today, we actually have implemented two different kinds of resource managers. One is a network resource manager, and the other one is a DTN resource manager. So the idea is that based on where your data transfers need to happen, you can actually coordinate these resources and provide you some guarantees in terms of end-to-end. So an example of this is the work we're actually doing with the LCLS. It's part of the XFL ECP project. So we've kind of demonstrated, the components here with the data transfer workflow and the Sense stuff. We're now working with NERSC to actually exercise the superfacility API as well. So where the Sense system actually controls the network and the DTNs, the superfacility API actually allows you to manage computing. And so we're hoping to demonstrate that this year, where the data workflow is actually able to coordinate both the network, disk, and compute resources. The whole motivation for this is to do things like fast feedback, where you want to be able to compute the results immediately after an experiment is run, so that you can come back and validate whether the experiment is running correctly. Right. So there's a lot of use cases that are potentially more generic, but this is the one that we're focusing on for this year. So, we talked about Sense being end-to-end. And so what it means is that you really have to deploy this across multiple domains. And so we've kind of started that activity where we've been working with the R&E community to deploy, the network resource managers as well as the DTN resource managers, either at the sites or exchange points or in other networks. And so this is just this kind of gives you a general idea on where the deployments are and who are we working with right now. We are looking at actively trying to extend this so that we can integrate, Rousseau and FTS into the workflow and understand how Sense can actually interact with that. And so that's an ongoing activity that is potentially going to be starting this year. All right, and this is kind of my final slide. So, all this is kind of great ideas, but really what happens is when you start talking about the bigger picture, you want to have a vision that essentially, that the other facilities and all that buy into. And so I wanted to introduce this. This is basically the ASCA Integrated Research Infrastructure Task Force. This was set up by Ben Brown, who is now the DOE's Office of Science ASCA Facility Director. Essentially, he put together a team that discussed about how we would build a seamless integration with, compute experiments and networking and things like that. And so we've been meeting for over a year now. We have a white paper. We've kind of socialized this idea with the facility directors, and it should be released pretty soon. And so this will be something interesting if you're interested in understanding where the vision is in terms of integrated research infrastructure and how we're looking to approach building something like a super facility. This will kind of give you a general idea in terms of a framework that we're thinking about. So with that, I am going to end and take questions.
Thank you, Shin. Wow, really very fascinating new technology. I'm sure there are some questions out there about this. So I don't see anything in the document, but we have a raised hand already. Doug, please go ahead.
Can you go to your last slide and then I'll type the question in for posterity. This obviously is ASCR centric, but the DOE Office of Science has data centers elsewhere that don't seem to be integrated, whether they be BNL, FNAL, or JLab, for example.
So the within the task force, the answer is no. However, we actually approached it from more a generic standpoint, right? In terms of if you actually had storage, compute, networking resources, how would you integrate that? And so this document is more a vision as well as a generic framework, right? There's a lot of devils in the details in terms of we talk about, hey, if you wanted to use an API, what would the API look like and things like that. Those are not addressed in this paper. This is more a high-level vision paper. And so I would suspect that, when it comes time to actually implementing some of the ideas here, there'll be a whole different set of groups that will be established to kind of tackle those issues.
Okay, thank you, Doug. Are there other questions out there for Chin? So I had a question on the, this edge computing stuff. Is it mostly light source communities that you're working with on this? Are there particular special requirements there?
No, I think what
applicable
is that the what we're seeing is that the light sources seem to fit into this real-time edge computing set of requirements, and so we've been able to kind of get traction in that area. But definitely, I think the idea is what we want to develop is, you know, these design patterns that can be adopted by other sciences as well.
Okay, great. I don't know if there's comments out there as to how this would apply in, in NP or for the new experiments. There's also been, I know, a lot of discussion about packet marking. How do you see that fitting in with the software-defined networks?
So you're talking, I think what you're referring to is the packet marking for the LHC blueprinting work. So the way they are approaching that is to look at commercial solutions, because they want to do end-to-end, packet marking and monitoring. And so not every network is willing to deploy an SDN solution, right? So that's kind of where things stand today. There's another set of activities that I didn't talk about that is part of the ESnet 6 architecture. It's called high touch stuff, where that might be, if you guys are interested, that can be another talk at some other time. But what we're doing is we're actually integrating, FPGAs and compute in our network to do, these interesting things that we can't really do with production routers today. And so there's potential for us to have a lot of flexibility in terms of what network services we can provide. But again, when you talk about packet marking and things like that, you really are talking about end-to-end multi-domain. And so you need to find the lowest common denominator in order for all the domains to participate in it.
Okay, thank you. We've got time for maybe another question before we let you go, if anyone is holding back out there. Okay, Doug, why don't you go ahead?
No one else will ask. You talked about your virtualized in-network caching that you're starting to work on.
Mm-hmm.
Do you know when you imagine you'll expand it to a slightly wider audience?
So we're actually actively looking at partnerships. There are a lot of considerations, right? Because this is a new service. We're not saying it's a production service as yet. There are some security challenges too, in terms of, do we just run your containers, things like that, right? And so I think the discussion is open and we're willing to engage, but we do want to set expectations, right? In order to be able to have folks understand, this is not production service. This is something that we're testing. We're trying to understand feasibility. If we think that at some point it is extremely useful, it may actually develop into a production service. So Doug, if you are, if you are interested, please feel free to contact me. We can kind of set something up and then discuss what the requirements are, and we can kind of tell you what the constraints and all that are as well.
Okay, thanks.
Okay, thank you, Doug. So if there are no more burning questions at this time, I'd like to thank Chin very much for this very interesting talk. We're looking forward to seeing all the new developments on the ESnet network. Okay, so I guess we will move on now to our third and final speaker of the day, which is Alastair Dewhurst. So Alastair completed his PhD with Atlas in 2009 on CP violation and B meson decays. And from then until 2018, he spent half his time serving in a range of roles for Atlas, distributed computing, including frontier conditions database coordinator, distributed analysis coordinator. And the other half of his time was spent leading new production service deployments at the Rutherford Appleton Lab Tier 1, which was the first large site to deploy CVMFS and which led the adoption of Condor in Europe. More recently, RAL was the first site to adopt erasure coding for data resilience on their Ceph-backed WLCG storage endpoint. Since 2018, Alastair has been the manager of the RAL Tier 1, where he's currently leading a major upgrade to the site networking and is responsible for the UK HEP community's data management evolution. He's the former chair of the WLCG IPv6, the deployment task force, and currently co-chairs the new HEPIX erasure coding working group. He's going to speak to us today about a topic that's been gaining a lot of interest in, especially in the HEP community, about the use of S3 in your network data infrastructure. So Alastair, welcome. If you'd like to go ahead and grab the screen. Thank you.
I'll start. So yeah, so I'm going to be talking about building a data infrastructure on top of S3. Now I know that this is a US group, so I thought I'd just do a little bit of context about RAL and what exactly we are. So the picture you see is actually, this is the Harwell Science and Innovation campus, which is where the Rutherford Appleton Laboratory is based, but also an awful lot of other things. It's around 270 hectares in site, and it's located 30 kilometers south of Oxford. And then we've got, so as well as having several high energy physics departments and things there, there's a lot of other things that are going on as well. So we host the European Space Agency headquarters. There's the Diamond Light source. We've got particle physics. We've got a neutron and muon source as well, and various other things also on site. And it probably doesn't come as much as a surprise, but there's been various new buildings which are not shown because they're so new, to do with research into infectious diseases and things, or basically a response to COVID. But I guess the summary is that while people may know me as somebody that's obviously just done the RAL Tier 1, the LHC, the actual RAL site does a large variety of different science projects. And while the LHC is the biggest user, I mean, on average, we use about 40% of the external network connectivity, the Tier 1 does, and probably roughly about 40% of the data activities in general. There is a very large other community of small users, and they are growing far more rapidly than the LHC growth rate is. So moving on, so yeah, so just a little bit about kind of strategy. Why is RAL doing what it's doing? So STFC, it supports the high energy physics, nuclear and space science communities within the UK, and it's got close relationships with other research councils which may have shared facilities. So within STFC, we've got a scientific computing department, and that aims to provide the computing resources, as in the scientific computing resources, not the desktops and things, for everyone within STFC, if we can do that. So we have bespoke solutions, such as there's the Jasmine data cluster, which is doing very data intensive stuff for the atmospheric people, which actually comes under space science in the UK because they get that from satellites. And then there is a general purpose OpenStack instance, which is very much kind of the core of the strategy. And that has grown in the last couple of years enormously. It's heading up to 50,000 CPU cores, 300 plus GPUs, and it's kind of increasing in size by maybe 50% each year. And then we do have an S3 storage, which I will be talking about in a bit more detail, which is Echo. That is also the same storage that does XRootD, as Andy was mentioning earlier, and it still does grid FTP, although that will be phased out shortly along with the LHC videos. And we've got a tape archive of the order of 200 petabytes of data. So there's a link to a recent HEPIX talk for more information about the storage that we do. I'm giving a talk at the moment. Can I finish the talk, please? Thank you. Sorry about that. So yes, and I guess the picture I've got on the side here is.
Look at me.
Thank you. Can I finish giving my talk, please?
Look.
Yeah.
It's fine. Look.
Thank you. Thank you.
Thank you.
Okay.
Cupcake.
Thank you. Can I finish? Thank you. Can I finish my talk, please?
Yeah.
I'll see you in a bit. Is everybody still with me? Yes,
Very
much so.
I apologise. They've just got back from the shop and they've got some new clothes and shoes. Sorry, where was I? So yes, so the picture on the slide of this is that we can't, people will need various bespoke solutions for what they're doing. And there's a whole range of things being done, whether it's machine learning, whether it's some data intensive stuff, whatever it is. And that's always going to be necessary to do. But that is almost, it's often extremely expensive, that solution. And then having kind of general purpose stuff that the scientific computing department can provide, which is basically infinitely expandable, means that people can, do what they need to do on their project, and then as they expand or whatever, they can move it to a different storage, which and different types of solution, which for a lot of cases are good enough. And then, but we're not getting rid of the other smaller projects, more bespoke, dedicated projects that are going on as well. Okay, so sorry about that. So moving on. So then IRIS, and I put it in UK because I know there's an IRIS HEP. So that's an STFC project which has been going for 3 years now, and it was 4 million a year, and it was to fund shared computing and services for the non-LHC community. And what we've shown here is that we've observed modest growth in so non-LHC grid usage. So people like June have come along, LSST, or the Vera Rubin Observatory, they're coming along with their data challenges, and they're making some use of the grid. But you can see from the plot that basically people are coming along and they want to use OpenStack and the resources on that. And there's been a massive growth in the resources as mentioned over the last few years. And also it's taken a while to catch up because storage is a bit more complicated, but the S3 storage growth is now, it's established and it's starting to grow strongly. And we've got many requests. We've got several multi-petabyte requests now for storage that people just want S3 storage, don't care about grid and other things, and to make use of that. So yeah, just to focus then on the S3 usage. So yeah, I've only got there's only 60 days here because the new monitoring came in at the start of February, but it was it's actually, I guess in the last 6 months, it's gone from a handful of terabytes up to about 340 terabytes that we've got now, where we've gone over 100 million files that are stored there, and there's of the order of 400 buckets and about 45 different communities with buckets that are using the S3 endpoint. So, and yeah, most of them are fairly small. They're of the order of a handful of terabytes. But one of the nice things is that it kind of S3 or the setup that we've got here just doesn't care about the size if they're small or if they're big. It's completely scalable in terms of the way that the interface works. Okay, so just kind of taking a step back and just to talk a little bit about the storage architecture. Now, this is obviously extremely dumbed down, and I'm talking to many storage experts here, so I kind of feel in some ways it's a little bit nice. But with an object store, what I guess the point I'm trying to make here is that you've got a bunch of storage servers and not much else. And they may be running daemons or etc. as well, but effectively they communicate with each other, and then you can get a client to talk to them directly, or maybe there's a gateway, or there's a cache, or there's some door to access it as well. But this is basically with an object store, that's what you've got. And if you've got things like Ceph will work like this, but also other things like Luster, even though that's a file system, if you kind of look at it and you're trying to set it up as a sysadmin, the first thing is it talks about the object store, which is the storage nodes, before it adds in the other components as well. So, and that's the kind of the next bit, that to move to a file system, effectively what you're then doing is you're saying, in a lot of cases, you add in a metadata server, and that's what the client can talk to if it's trying to, basically do operations that are looking at the file system. And then when it actually needs to get a file or do something actually with the data, the metadata server will talk to the storage servers, and you'll get the data from that. And then if you want to be even more fancy, you add in a tape system as well, and you've got yourself a hierarchical storage manager. So I guess what I'm trying to say here is that from the architectural point of view, having an object store, having S3 they're not the same thing, because you can have an object store and then add a metadata server and make it into a file system, or you can do other things with it. But if you've just got the raw storage setup with the object store, it is a significantly simpler setup. So, and this is what I'm trying to encapsulate here, that with the object stores, they offer advantages, disadvantages for both storage administrators and users. Now you can put an S3 API in front of non-object stores. So I'm fairly sure, although I'm not up to speed with it, but Dcache, you can stick an S3 interface in front of it. But then kind of some of the advantages of the administration an object store you miss out on, because you're administering Dcache and with all the bells and whistles it's got, and as opposed to just maybe managing a different service. But of course, the users get the benefits if they want them as well. So from the administrator point of view, if you are doing an object store, you do, and that's all you're doing, you've got a larger choice of solutions, one that might be able to fit. And it's definitely more scalable because there's no central database. There's, you literally can copy and paste your server builds just almost infinitely to provide as much storage as you need. And it is, well, because it's simpler, it is better suited to certain features. The one example being erasure coding here, because if you've got an object store and you're not allowing things like modifying the files, because S3 doesn't, you can delete your file, you can write in a new one. Because you don't allow that, well, that's actually something that erasure coding doesn't handle very well. If you've got to edit a file because you've got to recalculate the parity chunks, but if it's not allowed at all, you've got, it's not saying you can't do it if you're not using an object store, but basically something that erasure coding is weak at is not permitted with an S3 API, and therefore it's better suited. From the user point of view, again, the main advantages of S3 is that you can basically, if you've got a problem, you can often just Google that plus S3 and somebody has written some software to do it. And also, certainly compared to the grid and things, the documentation is fantastic. And because this is what the industry uses, you can actually go and you can read documentation from Amazon or whatever about exactly how to use and build your software on top of S3. And people like that because it's not, we're not having to provide that. It's not 4 years out of date on some, legacy looking wiki that nobody trusts. You can go and it's freely available. It's kept up to date by an extremely large worldwide community. And those are the really big selling points for users. Now, obviously the disadvantages, as I kind of alluded to, there's fewer features. So things like the modifying files, not allowed, that's not possible. And there are other, there's a range of other features that aren't supported with the object store. It's very much about you put your file, you get your file, and everything else you kind of, the user needs to control. And one of, I think, the things that I've highlighted here is that it puts more responsibility for security onto the user compared now. And you may have heard recently, I forget, it was in the news, exactly what company, but if there was a sysadmin for a particular company whose LastPass credentials got hacked, all of their S3, all of the company's important S3 credentials were in there, and it basically handed over the entirety of that company to the hackers to look where they wanted before they did their hack. Now, from the administrator point of view, actually you're still safe because the user losing their credentials is a problem for them, but not for the site. However, we work in an environment where the user blames us or the site admins when they make a mistake a lot of the time anyway. So it's kind of, if something was to go wrong with the user, it's going to splash onto the site, unfortunately, anyway. And obviously, we don't want them to run into problems either. So there is a bigger responsibility for security there, which I think it really should be noted because it's something that we've, is becoming much more visible. And with anything with S3 as well, there's no defense of obscurity like we have with the grid. I mean, no offense to Andy when he spoke about XRootD, but outside of the high energy physics community, it's not widely known. There aren't going to be people in the general population that know all about it and can take advantage of flaws and things in it. There, and yeah, I guess my main worry is that somebody just writes a bit of code, sticks it on GitHub, and forgets that they've put their S3 credentials in there, and somebody will just come along and swipe them and cause all kinds of problems. Okay, so just a little thing, just to highlight, and this happens to be this year's procurement that we have at RAL, and it's literally, this is it. We can just buy racks and install them of the storage nodes as we do, and they're all the same. Got a leaf switch at the top, a couple of Ceph head node type things, and then we've got a bunch of storage nodes. And overall, those 3 racks provide 18.4 petabytes of raw storage. And literally, if we needed more, we just buy more racks. And that's how it is. And I've got no concern whether if we needed to buy 100 petabytes, we could do that. If we only needed to buy, needed to buy less. So it is really, from a site point of view, very straightforward to do what you want if you're managing an object store there. And I guess because this was a network talk, I felt obliged to put in a network architect here. But yeah, and I guess what I was trying to say here, that we have connected, or we're in the process of, as was mentioned in this upgrade, where we're connecting the storage to a, not only externally well connected, but internally to give very good connectivity to the rest of the of all the other services that need it. So it can really be used as a center for shunting data, whether we want to share it externally or with various bespoke services in the department. Okay, so continuing then, so just to come back to then S3 and actually start focusing on the stuff that we're building on top of it. So why is S3 good? And the main selling point, if you weren't already aware, is pre-signed URLs. And what they allow you to do is, if you've got the secret and the access key, you can generate a URL to access the storage. You don't need to talk to the storage. You've got enough information with those 2 bits of information to generate it. And then you can give that to anybody you like, and they can then do that operation. And so it's really excellent if you're developing software for it, which your users can then do. It's less good if you've basically got end users that are coming along and thinking it's like an account, such as they've got like a username and password to an account, like if you logged on to a shared file system or something, and it's like, here's your username and password. It's not like that at all. And if people think that, they're going to be in for they're going to run into problems. But it's really good for people that want to develop things, because you've got all of that flexibility. Anybody that comes along, they talk to your service, you give them a pre-signed URL, they can get the storage, they can get access to the storage, or they can do the one operation that you permit them to do. So how is this actually now being used by the community? And this is kind of what I'm going on to. So a lot of the small users that we have, they've settled on rclone as a tool. And this is to basically, if they've got their data taking point and they want to just shunt data in and out, normally from a shared file system that they've got, where they're doing a little bit of their work, they need to either, they want to archive it, they want to share it with other people, or they've just, they've got an overflow. They can use rclone, transfer it to S3. It's a very simple setup. They've got there's a handful of lines of config that they put in their file, and then it's set up and ready to go. There is as long as they maintain, they need to put their credentials into their config, but as long as that's then restricted to a handful of hosts, it isn't much of a security concern at all there, as long as they're looked after properly. But normally they are, because they are part of an experiment set up at maybe some other site. And I mean, I tried to get some feedback on this, but I mean, all I'm basically getting is users saying it's great, and they can regularly saturate their bandwidth in and out of Echo, but overall we've got a much larger bandwidth than them. So that's normally a 10 gig link, or in some cases only a 1 gig link. So that is what a lot of small communities are using to put their data in and out of Echo. So well, what about something a bit more advanced? So one of the things that we've worked on, and what I would certainly recommend it if you are interested, just as something to learn from, it was the Dynafed project. So this was funded by the IRIS, as well as the IAM service that we have. And what this allows people to do is, if they're interested in getting or sharing data with other people once it's got onto Echo, so maybe they've used rclone to copy it in, they can use Dynafed, and you go to Dynafed and it will redirect you to IAM. So if you've got an account, with any EduGain institute, so US will be fine, you would be able to log in with those, and it would associate you with an IAM account. Now, with the IAM account, you can apply to a particular project. So whatever project that you're part of on S3, and then that would then, within Dynafed, that basically gives you browser access to everything in the bucket, and it can make use of like file system like structures. So if you happen to do your URL with slashes in it, it will make that into a file system structure. You can browse, you can highlight various files you want, you can click download. There's other buttons that you can do which will give you the pre-signed URL. So if somebody literally didn't have any account to log in at all, and the Iris one is meant to allow them, pretty much anybody to do it, anybody with a university account to log in, but even if they didn't have that, you were working with, say, maybe a commercial partner, you can send them the pre-signed URL and they can use that, or you can attach the pre-signed URL to a job or something you're running and leave it away. So this was a project, and it really evolved. I think there's the interesting thing with this was that when we started the DynFed project, it was about, oh, let's do TPC, let's do other things with it. But actually what users wanted was just a really simple way of accessing their data. And this is it. You go to a website, it directs you to log in with your university credentials, and then you've got browser access, you can highlight it, you can click download, and you can get the files you want. So, and very much, and the nice thing with this is all the credentials are held on the DynFed server. So as long as we keep, and we're in control of that, so as long as we keep that safe, users can be all around the world. They don't need to know the S3 credentials. And if they've got that, they can access the data. So from a security point of view, it's great as well. So what else are we doing? So another way that we're doing, and as I mentioned, that the cloud usage is growing massively. So and a lot of people, what they want is they want to be able to access S3 storage from their OpenStack VMs. And so what we're doing is we're implementing it. It's in pre-production at the moment, so it's ready, but we've not, and we're testing it at scale, but we haven't let users on it. But it's the Keystone service which comes from OpenStack. So the aim of this integration, it allows a Ceph cluster to provide Swift object storage for an OpenStack deployment. So you can go in to the OpenStack, via a web browser, you're doing the interface, and then you can request the credentials you need, which will give you Swift credentials or S3 credentials to access the storage. So sorry, I should have said, so if you're not familiar, Swift is basically the OpenStack equivalent of S3. It's obviously the native thing that OpenStack wants, and in some ways people think it's better because there's an open standard rather than S3, which is effectively controlled by Amazon, although I doubt Amazon will change it too much given how many people are using it. But effectively, the Keystone service does this. So this allows people to request their own user credentials for the Swift or S3 via OpenStack, so they can get away, and it also allows them to more easily access their buckets in their VMs. So it provides an authentication service and can use these to authenticate, and it means that we don't have to be continually, as sysadmins, handing out the credentials. If they've got access to OpenStack, they'll be able to create their own credentials once we've set up an account for their group or whatever, and given them some quota on it. Okay, so moving on then, just to talk about third-party copies. So this is something that, the models I've been talking about so far have been relatively small communities that can basically put all of their data many times over into S3, and obviously that's a nice simple solution. Whereas we obviously work in a larger community where we've got hundreds of sites that we need to transfer data to, so third-party copies are an important thing. Now, one solution that we did look at, and this was this DynFed project, was to use DynFed to do it via this fourth-party copy mechanism, where effectively DynFed, once it received an FTS transfer, could in effect SSH into one of the Echo gateways, and it would be doing wouldn't be doing a third-party transfer. It would literally be pulling the data to the gateway and then putting it into Ceph. But because it was on one of these data mover nodes anyway, that would be fine. And one of the kind of nice things with this was that would then allow us to support any, whether it was GridFTP, WebDAV, XRootD, any protocol that we wanted to, it could pull in the data and then write it to the Ceph backend. So it was tried, it worked in principle, but there were lots of little things when you try and scale it up, and there was never any real demand for it. So it was never taken past that. It is a way forward, and it is a possibility. But I guess these days I kind of wouldn't recommend it. And the reason why is that, well, I guess the main reason why is just with the DOMA TPC work that's been going on, this problem is kind of almost solving itself. All these other storage endpoints now are supporting WebDAV. That's kind of been standardized on it. So, and while things aren't working yet, there's so much progress with the community going on. So everybody should, within a few years, support WebDAV third-party transfers really well, and this would allow them to effectively, S3 will just be another endpoint, an FTS transfer can go in and copies can be done. I'm sure there'll be a few edge cases, but it very much feels like, the Dynafed solution that we looked at initially, it's just not needed in the long term because of the progress that the rest of the community has made. Finally, so one thing that we've looked at but not put into production as well is bucket syncing. So one of the things that we can do with S3 is sync pairs of S3 buckets. So and it's a very simple config change to do this. You can say I want to map as long as you've got the access credentials, you just say this bucket needs to be mirrored with this one, or whatever else that you're planning on do. And I mean, the key use case we see this for is for exporting data from SK from South Africa. So their data, the data taking facility that they've got is based on Ceph, it's S3. And they're already using the bucket syncing to do this between their equivalent of point one, where they actually collect the data somewhere in the middle of a desert in the middle of South Africa, and their proper data center somewhere, I forget which city it's attached to, but attached to a university in South Africa. So they're already using the bucket syncing, and then the idea would be, well, actually we need to sync the data up. We can actually just say, well, actually let's just sync these S3 buckets together, and that would move the data that way. And while this is kind of quite a step, that it is the kind of thing that I could imagine that could potentially feed into some kind of data lake model and things that we're working on in future, that there is a kind of, it's a bit like a back door, but you could actually say, well, yeah, there are ways of, from between different cloud storages, saying actually we're syncing these buckets. So Russia, or the brains behind the data lake, will know actually if I need to transfer data between these two, there'll be a bucket I can tell, move this data into this bucket, it will sync it across there. And it's a different type of, it does it in a very different way from using FTS, but in effect it is still just doing a transfer between two sites. And that may well be a good way of transferring between S3 endpoints in future, especially if they're supported by the same underlying technology, because you can be reasonably confident that they will work well. Obviously, the more traditional third-party transfers that I mentioned in the previous slide may also work as well. And that is me done. I apologise if the interruptions threw me off a bit, but I hope people mostly followed what I was saying there.
Thanks, Alastair. Yeah, that was no problem. Very interesting presentation. Do we have some questions out there for Alastair? So, well, people are thinking. So I'm curious. So first of all, how many groups and users do you have using the service at RAL? And in general, are most people within the communities using Ceph as the backend for this and relying on that? So is that sort of the standard way people are doing this?
I think there's two different. So the number of users that we have accessing S3, that's last check is above 40. So as in there's 40 different communities that have accounts and are putting at least some data into Echo. So quite a few of them may still be in the test phase, but we've got certainly more than 10 that are actually genuinely using it for their production use cases. In terms of the underlying support of the storage, I mean, RAL has adopted Ceph, and so I feel that it's very Ceph-centric view there. I'm well aware that there are other solutions for if you want a basic object, if you're just running an object store. There are a variety, and I mean, actually, the person that keeps educating me on this is Shigeki from BNL. He's aware of a variety, and of course, there's also a bunch of existing storage services which are like, okay, if you're interested in having an S3 interface, well, it's effectively it's a web server that you can add to your file system or whatever share service that you've got to make access of it. So yeah, I mean, of the community I'm in, yes, it's very Ceph-centric, but I don't, and it is certainly, what I can say is that I've certainly seen a wide variety of Ceph use cases. So it's used in the commercial sector, it's used in the research, but that's not to say that that other solutions aren't being used. And I kind of feel that when you ask a question like that, maybe don't take my word for it, because I know that my worldview is from a Ceph-based thing. So other people may be able to give a fairer answer as to what are the common technologies actually being run by sites in order to provide S3 endpoints.
So I was curious about the data integrity question. Andy brought this up earlier. So I think Ceph handles the data integrity on disk typically, right? But does S3 have some kind of functionality for integrity in transit that you know of?
No, I mean, other than, okay, so this is where my technical knowledge may be limited here, because Andy can come in and correct me, but effectively, I mean, if it's done via HTTPS, you've got the, because that's encrypted and because it's checking that it hasn't been tampered with, effectively a corruption. So as far as I'm aware, certain types of, corruption in transit would be picked up by that. Other than that, no. I mean, S3 does not offer anything else. I mean, you can store metadata with the files. So if you wish to say the checksum of this file is this, that's absolutely fine. But that's no different from attaching a bit of metadata to saying my favorite color is blue. It doesn't then use that. It's just, if you wanted to ask for that bit of metadata, it will return it. So you can store your checksums, but other than the standard checking that would happen with an HTTPS transfer, I'm not aware of anything. Well, S3 as the API doesn't do anything. The backend storage obviously have whatever system that they have in place for managing data resilience. Or data integrity.
Okay, I thought I saw Andy unmute there for a second, but
no, I did. I
you
mean,
answered.
what Alastair says is absolutely correct. Nobody really knows how good HTTPS is in detecting errors, but it should be sufficiently good. Let's put it that way. I haven't ever seen a number saying this is, how many bits it'll detect corrupted and how many it won't. That said, it's essentially an all or nothing thing, right? You get no correction on the fly. If there's a bit error, the connection is terminated. And then you have to start, and then it's up to the software to figure out how to recover from that. Yes, you basically, this is the sledgehammer approach to making sure you have data integrity in motion.
Thanks, Andy. I see Shigeki's been waiting patiently with his hand up. Shigeki, you have a question?
Summoned.
I'm a little bit ignorant of the use of object storage, so maybe this is a question that doesn't make any sense. But how are buckets utilized by your system? Do you dole them out to particular groups, or do they?
So, okay, you can think of a bucket as no. So you deal out accounts to groups, and then they can create buckets. Now, the way I kind of think about buckets is they're the kind of the compromise. When they first designed S3, they're like, okay, it's just an object store. There's nothing, you've got nothing at all. You put in your objects, you remember where they are, you get them out, and that that was too difficult to use. So the bucket is the kind of like, you get a one-level file system, so you can say, right, this will be, I'll put all my data for this project in here, or this project in here, and you can give certain properties to buckets. So you could make a bucket which is publicly available. So you could say any object that goes in there will by default become publicly viewable, or you can put a lifetime on a bucket. So you can say anything that goes into this bucket will last for 60 days and then be deleted. But yeah, I mean, the point is you can also do that on a file level. So you can put a file into a public bucket and say that's not public if you wanted to. So it's kind of, it's a default, but you can always override it at the file level. And the way to think of it is that, yes, when they went for we're just going to have an object store, there's going to be, nothing, we'll keep it completely scalable. They were like, that doesn't work. Humans need like buckets, literally to to put things in, that there's that one level of, okay, I can't deal with no organization at all. I'll have this one layer of organization. So, but you do see things that, you will have groups that have 40 buckets with not much in many, in a lot of them. And then other people can have a bucket with 1 billion objects in, and, either way, it's okay. It can be handled, and the aim of the bucket was not it was not to be a limitation. It was just humans need some level of organization, so here's buckets to do that.
Was that ever what is it, proposed as a tool for the user? I mean, I consider buckets as a natural way to organize collective data, which would be a nice way to push it back into a tape system, right? But does that come naturally to the user, or do you really, does it make sense to nudge the user down that path?
So I think, this comes back to what I was kind of saying about S3 in general. I mean, it's great for developers. And so when we're talking about, users and developers, if you were designing a tape system, I could certainly imagine a situation where you said, okay, logically, I want to make sure certain things are written to certain tapes. So you could certainly have a system where, you said, I'm going to have a bucket per tape. And, because if you think of a tape library, even if you've got, holds maybe up to 10,000 tapes, even if you've got 8 robots, I know B&L's got a big deployment, but you could have 80,000 buckets if you wanted, assign one to that. And if you were a developer and logically that made sense to you, and you're like, yeah, I'm going to put the data in buckets that way, and then have a mapping, you could do that. But at the same time, the buckets, you could also just have your own database, which says, okay, I'm going to make sure that this file goes onto this tape, and then it all goes into one bucket, and it pushes it. The buckets don't do anything in terms of where they are on the storage. Oh, well, okay, technically you can. So you could say with something like Ceph, if we've got SSD nodes and spinning disks, we could say, okay, when you create a bucket, you could say, actually, I want this on the SSDs. So you could have a situation where you created a bucket which was then allocated to a storage hardware that was notably different in performance to others, and then you would want to use it that way. But logically, the bucket doesn't do anything. It's not like a file system. There is nothing from the object store takes when it knows it's in a particular bucket. It won't do anything particular with that you couldn't do at the file level anyway. Does that make sense? Is that answering the question?
To a certain extent, yes, but I was sort of driving at a slightly different angle as a way for the user to naturally organize things. If it becomes natural for them, then as an HSM developer or as a tape developer, now that becomes a tool that they can use to push things onto a group of tapes, right? I'm kind of wondering if that actually comes out in the way people use the system, or people run the gamut of how they utilize the buckets, right? But it sounds like it can be used if so desired.
Convenient use for a bucket, go ahead. But I think that's the thing. The general assumption is that if you need to structure or organize your data in some way, have your own metadata database, which is doing whatever you need it to do, and have a pre-signed URL which allows it to go and get the data and move the data to where you need it to be when you need it.
Right.
But yeah, you may find buckets will be useful in certain situations when you're thinking about how things work.
Okay, thank you.
Thank you, Shigeki. Are there other questions for Alastair? Okay, if not, I don't see any on the Google page. So that brings us to the end of today's session. I'd like to thank all 3 of our speakers for this really excellent survey of data usage on the network from so many interesting perspectives. Our next, and we'll get the recordings up there for people presently. Our next session is scheduled for May 4th. The topic for that one is going to be user-centered design. And we look forward to seeing you all back there. So thank you for signing in today. And thanks again to all our speakers and all participants. Have a great day.